Hassan Mikkel, and this is my Lab 5 for Physics 2211. And I picked my experiment to be the Falling Slinky. So to start off, this experiment we're going to observe the movement of a falling slinky and how the center of mass is affected. And in terms of this experiment, the center of mass is going to be the bottom of the slinky because it is stationary, as the professor is holding the slinky on the top. So we're measuring the effect of gravity on the slinky, and we measure the movement in an app called Tracker, and then build a model in GlowScript using the information and the equations in the next slide. So some physics principles that we used for this experiment is the velocity update formula, the position update formula, gravitational force formula, and the drag force formula. So just to clear up some thoughts on the constants, negative g is going to be negative 9.8, the gravitational constant, and negative b is reliant on the experiment, which you find using trial and error. And the drag force pulls the slinky in opposite direction of the motion. So to find the drag force, it is negative b times absolute value of velocity, which is speed, squared times v hat. So here's the tracker video. So we put the origin as the very bottom of the slinky, the center of mass, and then measured it. And the video seems a little bit slow because the camera is recording at 300 frames per second. So that explains the movement of the video. And on the right, let's let the slinky fall. So the bottom finally moves at the end, as you can see. So the standard mass of a slinky is around 0.2 kilograms, and I gather the initial position from the tracker video along with the change in time. So for my GlowScript code, so I already listed in the last slide, the mass is 0.204 kilograms, and then the initial position, and the initial velocity is 0 because the slinky is at rest while the professor is holding it. And then j hat is pointing up in the y direction, and the proportionality constant for the magnitude of drag force, we find that through trial and error, and the reason it's so high for this experiment is because the frames of the video camera. So we built 2 while loops. So while t is less than 0.4333 seconds, the bottom of the slinky is stationary and it does not move. So we used these 2 formulas right here to calculate the net force. And by adding up the drag force and the gravitational force, we got net force. And after the slinky began to move, after 4.33 seconds, in about 0.2 seconds, we measured the rest of the slinky's movement. So we found the gravitational force, and we found the drag force. We used the formula that was 2 slides before, and then added them together to get the net force. So for the expected results, the graph moved exactly how I would imagine it to. It's measuring the center of mass, which is the bottom of the slinky. So as we stated earlier, the bottom of the slinky remained stationary till about 0.43 seconds, and then it began to move down once the top of the slinky fully retracted. And then the whole slinky in total moved down to the ground. So what does this mean? So the reason the slinky bottom remains still is because the tension pulling the spring up is equal to gravitational force. So while the professor drops the top of the slinky, before the bottom moves, the tension is still equal. That is why it remains stationary. However, when the top of the slinky becomes closer to the bottom and it gets closer and closer, the tension force becomes less, and the gravitational force is able to pull the slinky as a whole down, and it outweighs any other force acting on it. Therefore, the bottom of the slinky reaches static equilibrium and reaches the floor due to gravitational force. Thank you for listening, and hope you enjoyed my presentation. Goodbye.